Okay, welcome everybody. Today we've got Dr. Ying Liu.
Yeah.
She is a research associate as opposed to a research fellow, apparently, but from the School of Aerospace, Mechanical and Mechatronic Engineering from the University of Sydney. She has specific research interests in ceramics, functional materials, and ferro and ferroelectrics, topological domains and domain walls. But today, she's going to throw a bit of that all together and give us a presentation on her research. I'll hand it over to you, Ying.
Okay. Thank you so much for the introduction. It's my great honor to have this opportunity to present my work here. Today, taking this opportunity, I will summarize some of my most important work and compile it into this report. Over the past few years, I have primarily studied on the ferroelectrics and antiferroelectrics. My research has been focusing on the domains, interfaces, and nanoscale phenomena in these materials. My presentation today will be in the order of my professional development. It includes the research into the domains, interfaces in the ferroelectric thin films, the micro and nanoscale mechanical properties in relaxer ferroelectrics, and the ferroelectric phases in antiferroelectrics. A few key techniques that are crucial for my research include the thin film fabrication using pulsed laser deposition method, the microstructure investigation using scanning and transmission electron microscopy, the in-situ structure evolution and the micro-nanoscale phenomena, and the external stimuli such as heat, force, and voltage. And also the property tests such as the ferroelectricity and anti-ferroelectricity tests. Here are a few equipments that I have used. The PRD, the aberration-corrected TM. This one is an in-situ stringing TM holder, and this one is an in-situ heating and biasing TM holder. And the last one is a probe station for ferroelectricity measurement of the thin film sample. First of all, what's the ferroelectrics? When many people hear about the ferroelectrics, they may assume that ferroelectrics have a close relationship to iron because the prefix ferro means iron. But actually, ferroelectricity is named by analogy to ferromagnetism. Ferromagnetism usually occurs in materials like iron. Ferromagnetic materials show spontaneous polarization and spontaneous magnetization, and the magnetization can be reoriented by external magnetic field. They also show strong coercivity under external magnetic field. Similarly, ferroelectric materials show spontaneous polarization, and the spontaneous polarization can be switched by external electric field. And similarly, they also show strong coercivity under bipolar electric field. For most ferroelectric materials, their polarization can be directly determined by its atomic structure. For example, this is a typical ferroelectric material, the model of a typical ferroelectric material like titanate. And from this model, we can see that light here in yellow and the titanium here in red displays away from the center of the oxygen octahedral. And this displacement gives rise to the spontaneous polarization of light titanate. And this displacement can be directly determined using aberration-corrected TM. Here is an image of the light titanate, and from this image we can see that titanium displays away from the center of its surrounding light, and this displacement direction is opposite to the polarization direction of light titanate, and this is a titanium displacement map of the light titanate. So for we using aberration-corrected EM, we can image the polarization from unit cell scale. Ferroelectric materials have a wide range of application. Because they have very good ferroelectricity and piezoelectricity. They can be used not only in people's daily life, but also in defense. For example, they can be used in memories, micro actuators, ultrasound imaging, and energy harvest. The first part of the presentation today will be about the interfaces and domains in ferroelectric thin films. This part of work was done at the Institute of Metal Research, Chinese Academy of Sciences. And this part of work is my PhD work. And here are a few important collaborators in this work. And Professor Ma is my PhD supervisor. In recent years, as electronic devices become smaller, there is a need to incorporate functional electronic materials into these devices as thin films. But for ferroelectrics, there is a problem. That is, at the interfaces between ferroelectric materials and other materials, such as here is an insulator and here is an electrode material, the polarization decreased significantly. That means when the thin film size decreases to a critical value, the ferroelectricity may disappear. Here we have designed a bismuth-ferrite light titanate heater interface. This interface shows both the polarization discontinuity and also the valence discontinuity. We expected to see some unexpected phenomena at this interface. And here is a high-resolution image of the interface, and from this one is a out-of-plane strain map of this image. And from this image, we can see that there is a remarkable enhancement of out-of-plane lattice parameter. This suggests a polarization enhancement because for both BFO and PTO, there is a strong polarization lattice coupling. So to further prove that there is a polarization enhancement at the interface, we have conducted bright field imaging of the interface. For the bright field image, we can observe both the light titanate and also the light titanium and also oxygen. So according to their positions and displacement, and using the Born effective charge method, we can calculate the polarization at each row of the lattice. And we did observe that there is a remarkable polarization enhancement at the interface, and we can see here. And the polarization at the interface can be as high as twice that of the bulk value, more or less, a little bit less than twice that of the bulk value. Then we have grown thin films of different thickness. We decrease the thickness of PTO to 2 unit cell here, and we have observed that for all the thin films with 17 unit cell, 6 unit cell, 3 unit cell, and 2 unit cell, there is a remarkable lattice elongation at the interface, and all of them suggest that the polarization enhancement at this interface. To review the polarization enhancement mechanism, we have conducted EDS mapping and XRD analysis of the interface. From the EDS mapping, we found that the interface is very sharp and there is only limited diffusion. And from the XPS analysis, we found that the interface is oxygen depleted. This is the oxygen profile, and we can this is the interface. We can see that at the interface, the oxygen is depleted. From the EDS mapping, from the XPS analysis of the valence of iron, we found that at the interface there is a valence decrease of iron. Here is 3 plus, and here is 3 plus combined with 2 plus. Using the polar catastrophe model, we can determine that the interface is a light oxygen terminated interface. And according to the first principle simulation, we found that it is the interfacial, the oxygen vacancy near the interface that contribute to the polarization enhancement. According to our result on the bismuth ferrite and light titanate interface, we have designed a ferroelectric and electrode interface that is more important for electronic devices application. And we also found that in PTO it shows very high polarization, and even for the 3 unit cell PTO, the polarization is very high. In addition to the interface, the domains in the ferroelectrics are also very important in determining their property and applications. The flux chloride or vortex domains in ferroelectric materials have attracted a lot of attention in data. At the beginning, people using first principle simulation method to predict this kind of domains. For example, this 2 image using first principle simulation to predict that the vortex structure, vortex domain pattern in the PCT, nanodisk, and the nanorod. And then people using the piezo response force microscopy to investigate this kind of flux chloride domain pattern. But for the nanoscale domains, it is most useful to use the TEM to observe this kind of domains. For example, these 2 work, researchers using TEM to identify the half flux chloride domains in the ferroelectrics, and in this researcher using the TEM to investigate the full flux chloride domain patterns. For the full flux chloride pattern observed in the PTO, STO multilayer thin film, it shows strong strain inside the domains. As we can see here, here are the schematics of the strain state in the PTO thin film. And we can see is actually in each area of the domains, the lattice is not perfect, is severely strained. And here it shows the overall strain state in the PTO layer. Because the domain patterns in PTO layer is directly related to the PTO layer thickness, so the strain state is also closely related to the PTO thickness. Then we according to this rule, we have designed PTO, STO multilayer with adjacent PTO layer with different thickness. For this one, the PTO thickness is exactly the same in each layer, and we found in each layer the domain is exactly the same. And here is a model of the strain state in this material is fit very well. And then we decrease the thickness of one layer of the PTO into half thickness of the other layer. And we found the domain patterns has changed a lot. And on adjacent layer of the PTO, near the thin layer of PTO, it shows the upside curve of the polarization. And this one is clockwise, and this one is anti-clockwise. And here is a schematic of the resulted domain pattern. And for this From these two images, we can see this trend clearly. And using the phase field simulation, we further prove this result. Okay, next, the second part of the presentation is about the excellent mechanical properties in relaxer ferroelectrics. This work was done at the University of Sydney and in Professor Julie Kearney's research group. And here are a few important collaborators. In material science, people's basic understanding of materials is that metals show excellent plasticity due to the metallic bond, while ceramics are usually brittle due to the covalent or ionic bond. Here are two examples of plastic deformation in metal nickel and brittle fracture in ceramic silicon. There are some rare exceptions to this rule. Some crystal with a spatial structure show some plasticity, and also some nanoscale material show some plasticity due to lack of defects. Here in our sample, we have observed some hints that suggest that it may show very good plasticity. The first one is this. This is a TM sample that is very thin. Is like a wide sample. This edge is very thin, and then it gets thicker and thicker. And from this edge, we can see that there is this kind of dark and bright contrast. And from the around direction, we see that is curved. The thin edge is curved. That suggests it has deformed severely. And also from TEM samples, we found that there are quite a lot of entangled dislocations, and for both the dislocations and the severe deformation in the sample, this suggests that the material show excellent plasticity. Then to extract its deformation data, we have conducted in-situ stringing tests on this sample. This is a TM holder, in-situ stringing holder for in TM. This one is an in-situ stringing holder in SEM. And we prepare a sample. This is nanopillars here from very small to big. Prepare these pillars for compression tests, and this the dog bone structure for tensile tests, and this cantilever for the bending tests. We started the bending. We started the compression tests from very small sample. This is about 150 nanometer in diameter. And we can see when we compress the sample, there is a lot of slip bands appear, and that means there it shows excellent plasticity. Yeah, and it does not crack after removing the indenture. Because in perovskite oxides, strontium titanate is supposed to be to show excellent plasticity. Here we compared our sample and that in strontium titanate. We prepared samples using the same measures, and we found that after compression tests, most strontium titanate get cracked. But for the PIM, PM, and PP, our sample, it shows severe plastic deformation. Then we have go to a pillar of thicker of bigger in diameter, and here is a 2 micrometer in diameter one. And we can see it also shows severe plastic deformation. Yeah. Here is another example of plastic deformation in the big pillar. Now is the elastic deformation. And now it gets started, the plastic deformation, if you can see here. And after removing the indenter, it didn't get cracked. Okay, after the deformation tests, we have filtered thin the pillar into thin foil to observe in the TEM. And here is a TEM image. It shows that there is a lot of dislocations here. And by magnify this image, we found those dislocations are climb dissociated pairs of partial dislocations with a Borgus factor of 0.011. Then we have also conducted tensile tests. In the tensile tests, we didn't observe obvious dislocation accommodated deformation, but we did observe that the tensile strain reached 4%. Then we have conducted binding tests, and similarly, it also showed very high deformation. And here we see there is a significant drop of the load, which suggests a plastic deformation. And by fusing the cantilever into TEM foil, we observed there is a row of dislocations at the root of the cantilever, and the dislocations is of the same type as that compression deform the pillar. They are both the clamp dissociate partial dislocations. The clamp dissociate partial dislocations is not very common in the room temperature deformed samples because dislocation clamping requires point defects to migrate to or migrate from the dislocation course. For the point defects, it is more common to be vacancies and interstitials. But among perovskite oxides, vacancies are far more common than interstitials. So it is suggested that there are quite a lot of lead vacancies or oxygen vacancies. Then using the first principle simulation, we calculated the energy of the oxygen vacancy PI and PMNTT and the lead vacancy PI and PMNTT. And we found that oxygen vacancy decreased the system energy and lead vacancy increased the system energy. So there must be a lot of oxygen vacancies in the system. And according to the brittle ductile criteria of the material, that is BG ratio, we calculated the BG ratio of the PIM PMMPT and also the oxygen vacancy reached the PIM PMMPT. And we did found that for the oxygen vacancy reached the PIM PMMPT, it shows it have a higher BG ratio, and the higher BG ratio it should be more ductile. Then using experiment, we have conducted compression tests of magnesium doped PMPT, which is oxygen rich, and sodium doped PMPT, which is lead vacancy rich, and found that the oxygen vacancy rich, the pillar is more ductile, and while the lead vacancy rich, the sample is more brittle. Okay, the third part of the presentation is about the ferroelectric phases in antiferroelectric laser connect. This part of work was done at Catalan Institute of Nanoscience and Nanotechnology in Professor Gustavo Catalan's research group. And here are some important collaborators in this work. First of all, what's the antiferroelectrics? Just now we talk about ferroelectrics. For ferroelectrics, the polarization, the electric dipoles is along the same direction. But for the antiferroelectric, in the same unit cell, the electric dipoles along opposite directions and with the same magnitude. This is a hysteresis loop of ideal antiferroelectric materials. Under bipolar electric field, it goes to a antiferroelectric to ferroelectric transition. And this antiferroelectric to ferroelectric transition accompanies with a large charge storage and a giant volume expansion and a temperature drop. So it can be used in high energy density capacitors, in high spring actuators, and in electrocaloric cooling. We have grown PTO thin films on strontium titanate, and we have obtained a very high quality thin film. Is epitextural growth and with the surface very flat. Here is roughness is about in 3 nanometers, and this thin film is about 200 nanometers. And the dielectric measurement suggests it shows antiferroelectricity. But for the hysteresis loop measurement, we found that there is an obvious remnant polarization when the voltage is 0, and when the external voltage applied become bigger, the remnant polarization become bigger, and the hysteresis loop become very like that in the ferroelectric materials. Then using piezo response microscopy, we apply voltage of positive 10 watts and negative 10 watts. We found that the amplitude show an increase, and the phase show the upside about 180 degree, which suggests they show ferroelectric like behavior. So to understand what happened in the material, we have conducted TM observation, and we found at the interface between the PCO and the electrode, there is a layer of this kind of ferroelectric phase with a polarization along one main direction. It's like up, but with a smaller down. And these two arrows shows the upside electric dipole direction. In addition, we have observed another ferroelectric phase. Just now the ferroelectric phase shows up like smaller down, and for this one is shows like up down up. If we view this as up, is up down up, and in this phase, it can be a few layer of this kind of small unit cell, small unit. And this small unit is actually a translational boundary. So what's a translational boundary? Is when the crystal, one side of the crystal and the other side of crystal has a phase difference, then there is a phase translational boundary. For example, for this one is a perfect PCO, and if we move the other side of PCO to the left side of 1/4 of the unit cell, then it form a half translational boundary. If we move half the unit cell, is a pi translational boundary, and this one is a 3 half pi translational boundary. This is very common if it is only one such unit. It's half pi translational boundary, or this pi translational boundary, or 3 pi translational boundary. But if it is goes to 4 such unit, is not zero, because 4 such unit can be perfectly replaced by 3 perfect antiferroelectric unit cell. So it must be such such lattice have a lower energy than the antiferroelectric phase, or have a slightly lower energy than antiferroelectric phase. Here we have also conducted ITPC observation of the new ferroelectric phase, and here is obtained ferroelectric model. And also we found even for the dipole arrangement is the same, like here, here and here. We found the dipole arrangement is the same. The middle one is to the left, and this to the left, and the satellite one is toward the right, and this right. But their polarization can be opposite. That means we can the polarization can be adjusted by the magnitude of the dipole, but don't have to change the direction of the dipole to convert the overall polarization direction. This is the essential difference from that of ferroelectrics, in which the polarization direction have to be switched when the ion displacement direction is switched. Under electron beam irradiation, we found that the translational boundary, or here the ferroelectric phase, can be created or moved. For example, in this image A, there is no translational boundary here, but there is a translational boundary here after electron beam irradiation. And here we can see here is the straight, and after electron beam irradiation, it becomes band. Also, we found that the heat treatment may influence the create this kind of translational boundary. Here is a as prepared TM lamellar, and this one is the same lamellar, but after 150-degree heat treatment. We found there appear a lot of translation boundary near the domain wall. Here is a domain wall. And after 200-degree heat treatment, the translational domain wall further grows. And recently, after I moved to University of Sydney, because we have now the in-situ TM holder, here I have conducted some in-situ biasing and heating experiment on the sample. And here is a video of we first apply heat to 150, and then we apply the voltage to 40 volts and keep for 5 seconds, and then remove the electric field, and then remove the heat. And we can have a look at the video. And now we are heating, and there is a translational boundary here. And after heating, there is a domain pattern change here from one orientation to another orientation. And then it started to apply voltage. And then after removing the voltage, there is a lot of translational boundaries form, and at the beginning it forms more, and after a while it disappears some and keep some left. Let's have a look at again. And here we are heating, and then we apply voltage. Because it's from very low voltage to higher voltage. At the beginning, there is no phenomenon. And now it is almost the most. And then we remove the voltage. Yeah, we see there is a lot of translational boundaries formed here, and this part of domain increase, some of the translational boundary disappears. Okay, just a summary of the presentation. The first one is we reviewed interface charge discontinuity enhanced ferroelectric polarization at the bismuth ferrite lattice interface. The second, we plus closure domains. And the third, we observe the excellent deformability in the relaxer ferroelectric PIM, PMM, PT. And the fourth, we found two types of ferroelectric phases in archetypal antiferroelectric light-connect. Okay, here are some important findings, and all this presentation is from these papers and some important collaborators in my research. And take this opportunity, I would like to advertise for the journal Microstructures, and it's totally free this year. So if anybody is interested in. Okay, thank you for your attention.
Thank you, Ying. If anyone's got questions, just put them in the chat or just unmute yourself and ask away.
Can I ask a question? Thank you, Ying. It's a very wonderful talk and beautiful data.
Thank you.
I just have one question for the antiferroelectric project,
Okay.
the last one.
Yeah.
So I think initially you showed the big picture of the polarization, like the displacement map.
Oh, this one?
Yeah. So I was wondering, have you tried like different thickness, the sample with different thickness? Because I noticed that like away from the interface, it's more like a up and down, like anti-parallel polarization direction. But when it's close to the interface, it's more like a 90-degree domain structures.
Oh.
So
yeah.
I was wondering that if you apply mechanical force or change the thickness, is it possible to see some, I don't know, flux closure or something like topologic configurations?
We did observe two types.
Yeah.
This kind of this kind of like a stair like this kind of 90-degree, and also this kind of with different magnitude.
Yes. So I just wondering, like with the polarization change or when it goes to like a smaller size.
When it goes to smaller size, we tried I growed a film of about 10 nanometer, and we found that it's more or less ferroelectric base.
Ferroelectric?
Yes.
Okay.
Yes.
So I mean, like the antiferroelectric phase is like related to its thickness. When it's...
Yes, when it goes to very low thickness, it's reported to be more like a ferroelectric phase, and from my result, it's also more like a ferroelectric phase. And there is these two types. One is the like ferroelectric phase, and another one is like ferroelectric phase. It is exactly dipoles along the same direction.
Okay. Thank you.
Thank you.
Any other questions, guys?
Yeah. Hi. Hi, Ying. This is Nagi. When you looked at those pillars and you say is elastic deformation, plastic deformation, how do you know that? You just showed us some video, and what signature are you looking in plastic elastic deformation?
Normally it is supposed to be if the string can be recovered, it's supposed to be the elastic deformation, and if the string cannot be recovered, then it's supposed to be plastic deformation.
No, I understand that, but when you showed us the video, like for example, if you play one of the videos,
like this one,
and then you said, okay, here it is plastic, here it is elastic. So what happens? What are you looking over there? Also, when there's a kink, you say it is a plastic, is it?
Yeah, when in this part, when the stress strain is more or less the a straight line is supposed to be elastic.
Elastic, yes.
Yes, when the stress strain curve become banded, it's supposed to be there is some plastic deformation happen.
Okay, but then afterwards it again goes back to elastic, is it?
Sorry.
So what happens? Can you keep progressing this video?
Yes. Here you mean from the video?
No. You can keep progressing that. You're doing what I want. Okay. So now it's completely become plastic, all of these regions?
We can assume that is plastic because there is always this kind of stress drop. That means there is some slip band form. Yeah.
Okay, yeah, that was my question. Thank you.
Thank you.
Any other questions? Oh, there's no more questions, guys. Let's thank Ying for an interesting talk.
Thank you. Thank you.
Thank you very much, Ying.
Bye.
Bye, everyone.
Thank you.